Hello again, YouTube. Sorry for a very long delay. I suppose we had a festive period. It's the Happy New Year. I think it's the first of the new year. I've been relaying out, as you can see now, this is the cinnamonBun, and I've added USB. So I've got USB host. So this is a Type A connector, which isn't soldered in, obviously, and a USB micro. So this cinnamonBun can be a device, a USB device. And I've got the couple of LEDs and the switch that we previously messed about with Morse code for. So I want to make, as I haven't done a video for so long because I've been trying to get things tested. As you can see, I've still got wires hanging off here testing with oscilloscopes and stuff. So I decided I'd do a quick test of soldered on a USB micro connector, and we're going to do a quick test of a USB device. And I'm going to try and keep this short, and obviously that's not the simplest task to keep short, but we're going to try and do it in less than an hour, because if it gets longer than an hour, this is going to get ridiculous. So the easiest way to get from A to B is to use a project that's already there, that's been provided by Microchip. So I've got the Microchip MLA installed in /op Microchip MLA. I'm using Linux, so if you install it on a Windows machine, I don't know where it installs to, but that's where it is on my machine. So I know that Microchip's projects have a file called usb_config, usb_config.h. So if I find those and print them, I want a good project that I can use, and I'm looking for keyboard really, because I've got a button and a switch, and what could be simpler than a little keyboard? We may a one button keyboard isn't going to be a lot of use to anyone, but it's going to confirm that whether a USB is working. So sorry, inside firmware we have, well, the first thing is demo source, which is going to be platform independent source, and then the rest of these directories are all based on a specific device. Now this Explorer 16, that Explorer 16 project, obviously these are MPLab X projects because they end in a .x. That Explorer 16, obviously, it's actually running a DSPIC33 EP512 MU810, whereas mine is an EP256806. So that's got more flash and is a higher pin count, but it's the same family. So that project is going to be very similar to a project for the cinnamonBun. So that's our template project. So if I actually open that project, /opt Microchip MLA, I think it was apps USB device, head keyboard, and that's us. So all I'm interested in is the source files that it's including. Right. So actually let me create a new project, and this is going to be my keyboard, and it's on a DSPIC33, sorry. And we're going to use the PIC kit 3, and we're going to use the XC16, and we'll call this USB keyboard, for want of a better title. Right. So now that's going to have created, yeah, USB keyboard. Now I like keeping my source code in a directory called source. So if I copy that was the platform independence code, so I'll copy that here, and then we want the EXP16 we'll take all the C files out of there, and we'll take all the header files out of there. Now the buttons and LEDs are in BSP, so BSP, this is an Explorer 16 and it was a DS PIC 33 EP 512 MU. Right, there's buttons. So if I copy, we're probably going to change those files. Buttons is there and LEDs is there as well. We're going to change probably because their platform is going to have a totally different setup to ours. Instead of, I've got a couple of LEDs and a switch on a Vero board. I don't know what the Explorer 16 has. So app device, app LED, app device, app LED, buttons, LEDs, main system, have all those. USB descriptors, USB device, USB descriptors, I haven't got device. USB device, device head, I have events. So there's 3 files. USB device, which is a framework USB source file. So I assume the others are there as well. Now I don't want to copy those. Those are they're actual framework files, so I don't really want to mess with those. So I'm not going to copy these into this directory in case I then end up editing them by mistake. So they're framework files. USB source. So we want device.c. We also want device head.c and HAL. I just copied them when I said I wasn't going to copy them. I'm going to create a symbolic link. Gone too far. No, I can't make them unwritable. I want to write protect them, but they're links, so it's not. Now we'll go with that. So that should be all our source files. So now I can actually just get rid of this project that we're copying and add all those source files into our new project. So now the chances of us getting this to build first time are probably pretty slight, but let's get started. That's a header file for the wrong microcontroller. We'll just use xc.h, which is the magic compiler or include file, and let the let MPLabX sort out what include file we should be pulling in, as opposed to no such file usb.h. usb.h would be I imagine that is I imagine that's a framework include file. So yeah, if we add an include path of that and add that to the GCC preprocessor options, right, I will run that and see how far we get now. No. usbconfig.h is, that's in our local directory. usbconfig.h, we haven't got that in the include path either, so we have to add GCC SRC. Device local. That must be a framework file as well. Oh, we could add that to our include path, I suppose. We're getting there. So LEDs, this was obviously going to be a problem because the Explorer, whatever it has, doesn't have what we have. Now we've got two LEDs, so if I do a search and replace of D3, and we've got a LED on D0, so we'll just replace. That's us. and D4 will change to D. We've got a lead on D1. That's us. So obviously our lead on D0 is on. And we want tri-state D. And get rid of all those others. And we can get rid of all these. And I should edit all the comments, but we're in a hurry. We better have a look in leads.h and see what it's doing. It's got a leads count 1, 2, 3, 4, 5, 6, 7, 8. We're only going to have 2. Unknown configuration setting, that will be for a different microcontroller than the one we're on. And there's no analog select. Actually, sorry, there is no port A on the 806, which is a smaller pin count. LED 4 and LED 5. We'll just call them LED 0 and LED 1. Kind of a fluke that we have 2 LEDs on the little board. LED D4. I think I've just changed that. Yeah, I'll just build again. And the buttons. We've got one button, so this is going to be... And the button is on D2. So if I do S3 and replace it with D2, that's us. So we're on D2. And there's no analog select on D2. So that should all be good to go. And we'll have to go into buttons.h and see what it's... D2. D2, D2. They only had one button as well, or they only used one, so button 3 again. Let's build again. Oops. There is no analog select. I think that's it. I think that's it. Right. Back to main.c. The one thing we've got to keep track of is during system initialization, the system will have to set up a clock. So basically they're running this Explorer platform that this project was for, has an 8 megahertz crystal. Now the cinnamonBun has a 16 megahertz crystal, so the timings are going to be off. Now the maximum of this microcontroller can go up to is about 60. Well, if you don't go above 85 degrees, I think you can go up to 70 or whatever, but 60 is pretty much it. So now that FCY is the instruction. And that is FOSC divided by 2. And FOSC is equal to crystal times a multiplication factor m then divided by, there's a pre-scalar or a pre, actually if I bring up the data sheet, I have the data sheet here. And that's in the, I actually have it in the oscillator section, right? So this is the oscillator. It's quite a, there's a better diagram down here. Right, so this is the formula I've just given, that the oscillator frequency coming out here is equal to the frequency coming in divided by, there's this PLL pre is N1, and this is going to give us a clock frequency here, FREF, between 0 and 8 megahertz. So obviously when they had an 8 megahertz, they were calculating it as, so you've got 8 meg times, they've set m is equal to 60 divided by N1, which is the pre, that comment is wrong, check that. Yeah, N1 is the pre. It doesn't matter, they're both 2 I suppose, but yeah, we're not going to be using that. So 2 times 2, so that's quite simple in your head. FOSC is going to be 2 times 60, which is 120 meg. So we're going to do the same thing with 16 meg. And we can actually multiply it by 60 as well. But our pre will have to be, because of this constraint, if we keep things the same and divide by 4, and change the pre to 4, and that would imply that this is going to be 2, and that's going to result in the same thing. So 16 meg divided by 4 divided by 2 is 2 times, just basically the same thing. So I should change that comment. I'm not changing comments anywhere, but I better do it here. That actually doesn't really make any difference to the device. It's going to be running at instruction frequency of 60 megahertz. But what's more important is the auxiliary clock which runs the USB, and that has to be at 48 megahertz. And that must be set. I'll remove that line. Right, this is auxiliary here. And again, we've got an input. They've got an input of 8 megahertz. We've got an input of 16 megahertz. And it's pretty much exactly the same phase lock looped circuit. So this is the auxiliary, which is exactly the same thing, except they haven't put the post divisor N2 into this diagram. And the constraints are different here. So we've got 3 megahertz, between 3 and 5.5. And well, our constraint here is going to be that we want, well, we've got a constraint there. We've got to have 60 megahertz, between 60 megahertz and 120. But then there's a divider here, and we want out 48 megahertz for the USB. That's a strict frequency that we have to have on the auxiliary clock. So they have done it all in a oneer in this register, which I'm not a huge fan of. Because, well, not a huge fan of it. I like bit fields, and I like the fact that you can look at the code and see what you're setting. So they've set, I'm just going to copy what they have set for that register and amend it as we have to. So there it is, ACL. So the top bit 15 is ENAPLL. And they've set it to 0. The next bit, cell, why is it not giving me not giving him a chance? That is bit 1 of the top nibble, which they have set to 1. And the next is AOS command. And that's bit 0 and bit 3. That's 0. ASR. ASR is bit 2. That's set. And the next bit is that post. So we've only got 2 left. Post. ALL post. ALL post is in the top nibble of the lower byte, and it is set to C 110. and the pre is the lower, and that is set to 1. So the two we're really interested in, well, we're really interested in this one as well, because this is the divisor. Actually, the multiplier. Not sure why they call it that, but we'll go with that. So post has a value of 110, which is divided by 2. So post is n2 and it's divided by 2. And pre is n1 and it's 001, and that's divided by 2 as well. And then the multiplier, which is in that div, I don't know why they call it the divide, well, yeah. It is set to 111 if we were talking binary. So that's multiplied by 24. So for the 8 megahertz clock, they had 8 times 24 divided by 2 times 2, which is 2 times 24, which is 48. And if we just change it to if we go back up to the diagram, that's the auxiliary. There's a constraint here that this frequency has to be between 3 and 5. So if we just change N1 to be 4 from there too, that will leave it at 16 meg times 24 divided by 4 times 2, and that again is going to be 16 divided by 4 is 4, divided by 2 is 2, 2 times 24, 48. So that's us. So now all I've got to do is change this one value, the pre, is, we want a value of 4, which is 011. Yeah. So that should be us. So if I now, I'm going to power this off, well, I'll plug in my PIC-3 and power up the board off the USB and do a very quick program. Sorry, I don't have a USB cable plugged in my computer. I'm not powering the device. Too many cables. Try again. Right. So now if I get rid of the pick kit 3, I'll plug on our little test board, and actually just to keep track of this, I'll put this always on top. And I want if I do that, if I do demessage, ugh. What did I just do? Sorry. I don't know what I just did, but I just gave keyboard input where I didn't want it to go. Now, is this always on top? It's always on top, right. What I want to do is demessage -W. This is Linux, so I just want to see what's happening on the Windows or on the USB devices. So if I plug this in, actually it's already programmed up and run, so it's come in as a. So there we've got, it's showing up on demessage. If I do an ls USB, I've got 2 microchip devices, one of which will be the PickKit 3. Yeah, and the other one is this spurious keyboard. So now there's going to be a lag between my pressing a button and what you see on the screen. So if this works, yeah. So that's not the best keyboard in the world ever, but my USB device functionality works. So I'll call that a win. So that's it. I'm not sure how long that took, but we'll find out when I go to upload it. The one thing about this is well, we've actually implemented a useless single key keyboard very quickly. Hopefully I've done this in less than an hour. We've actually learned nothing about USB functionality. We've not done anything that's of any significance. The only thing we've learned is that it's got a strict, the USB module has a fairly strict requirement in terms of frequencies it's using. But it's an example project, and it is what it is. Hope you learned something. There isn't much to learn because we haven't, you haven't learned anything about the messages being passed back and forward by USB. But it shows you how easy it can be using library code to create a device, albeit a useless device. It's a starting point. The this code is, like I say, it's just in the Microchips MLA, so you can download that from Microchips website. It is under an Apache license. As far as I know, most of their library MLA is an Apache license, but I'm not too sure about the licensing. I'll leave it there. Thanks a million for watching, and I'll see you again soon, hopefully.